welcome back. Lecture number 2. And maybe you have had an opportunity to look at the iTunes video, and everything worked fine. I'm glad to report. So let's get started, okay? So today I want to discuss basically the some phenomena that are related to viscosity. It's a very important property of fluids called viscosity. So let me start with this video. Have you seen it? You have? How many? You haven't seen it? Yeah, that happened. Okay. Let's see it again. That's Spanish, by the way. Okay, so walking on water. So what's going on there? How can we explain what's happening there? And basically the fluid that you see in that pool is a mixture of cornstarch and water. Cornstarch and water makes this very particular mixture that flows like you see in that next movie, but when you stress it, when you apply a shear stress, it behaves like a solid. So what's going on? I have one more, my favorite. In fact, there is a multitude of videos like this that you can find on YouTube and different experiments. There's one with little Einstein doll that is jumping inside the speaker, and so on. So what is going on? How can we explain that? Well, so we see that the mixture of cornstarch and water is really behaving like a non Newtonian fluid. We have the situation that if you just let it stand still, it will flow. If you apply shear stress, it basically hardens. It becomes more viscous. This is the property of a shear thickening fluid. When you apply shear, it becomes thick, like the name says. It becomes more viscous. Okay? Now, in this case, really, cornstarch and water is not properly a fluid because it's not just one material or one element. It really is a mixture, a suspension, where the corn the starch, the cornstarch, or any other form of starch, many vegetables have starch. They store energy in starch. It's a polymer. And the interesting thing is that the explanation to this behavior is, you can read some explanations and they might not completely agree with each other. So you will hear some people say that this is because the polymer chains have some shape and they kind of sort of become tangled as you press the material. This explanation, although some people are very convinced of it, doesn't really explain for the fact that that the starch appears in really small granules. They're not molecules of starch just floating around in water. They're actually little granules. So the explanation that makes more sense is that these particles are sort of floating in water, and in a right balance between the water and the starch particles, there is a thin layer of liquid in between the particles that acts as a lubricant, so it can flow. As you press it, the water in those interstitial spaces gets pushed out, squeezed out, and the particles become in contact with each other so that the starch now acts as a solid. So here is a picture of what starch granules really look like. Each granule, in fact, has these molecules of the polymer inside in an arrangement, but they are particles, okay, of that sort of micrometer size. And when you squeeze it, the water comes out, and it's a similar effect like when you step on sand. You're familiar with this when you step on sand, on wet sand. As you lift your feet, there's like a dry footstep behind you that quickly gets moist again, right? So that same effect, you can perhaps see it in this picture here under the feet of this person here, that there's like a dry spot where the pressure has squeezed out the water. That is the explanation that is more makes more sense. So you know why this non-Newtonian behavior arises. So that is a shear thickening fluid. We've made a picture last class of a plot between the shear stress and the rate of shearing strain, and you saw in that case the slope of that curve for a shear thickening fluid would have a slope that increases, right? But other fluids are shear thinning. They become less viscous as you apply shear. Here's an example of a very interesting phenomenon. And again, I'll ask you to watch this one, and I'll be quiet while you do, so you can pay attention. I think this one just has some corny music. I don't remember if it has any. It doesn't have any audio. I took it out, I think. There. This was first this phenomenon was first observed by K. That's called the K effect, and he wrote a paper, 1963, simply saying, "I have observed this. I cannot explain it." So let's see step by step what is happening with a high-speed camera. Because this happens very, very fast, it's very hard to see it with the naked eye. But nowadays, there's this very fast speed cameras that allows you to record such a phenomenon. This is a video from the University of Twente, if I'm not mistaken. I will put some credits, proper credits in a document for you to find the original video. And they published a couple of papers on this, explaining this phenomenon. And it's a very simple experiment that you can actually do at home. This is the stable version. And another interesting aspect of it, it acts as a light guide. In this case, a laser beam is shining through the jet. And here is a high-speed picture of that, of the end result, with different colors. So what is happening here? So the K effect occurs when you have a thin stream of a shear thinning fluid that is poured onto a dish. The first thing that happens is, well, what you're used to seeing when you pour honey or any material. A heap, a pile forms, and the falling jet curls into all sorts of shapes and just forms a little pile that stretches out. But when the geometry is favorable, you can get this jet slipping and jumping out, like we've seen in this video. So what is happening here? Here is an explanation with some pictures, step by step, of what is happening. First, in the first picture, we have the formation of this heap, this little pile of the viscous material. You're used to seeing that. In picture number 2, we see that there is the ejection of this thin little streamer that in fact is kind of like a lasso shape, where one end of the lasso shape is still attached to the pile, to the heap, and the other one is directly attached to the falling jet of fluid. Okay? The jet that is slipping and shooting out starts increasing in angle, as you see in figures 3, 4, and 5. It increases in angle until basically the end of the K effect happens when the streamer just hits the incoming jet, and they just interrupt each other, and the whole thing falls apart momentarily. So here you have a picture, a little close-up to the beginning of the K effect, when you have this little lasso shape. And then here you have another picture that shows the streamer as it is shooting out. Now notice something very interesting, which is that the diameter of the falling jet is slightly smaller than the diameter of the outgoing jet. Did you notice that? It is pointed out in the movie as well. What happens here, the explanation that is given in this paper, is that for a shear thinning fluid, as the jet falls in the heap, it forms a little dimple, a little spoon-shaped dimple, where, you know, the pressure of the falling jet hits. The shear that is being applied there in the dimple forms a thin layer of less viscous material, which acts again as a lubricant and forms this little thin layer of lubrication so that the whole jet just bends and shoots out. Because there is friction, of course, in that layer of thinned material, there's some viscous dissipation. There's friction. Whenever there's viscosity, there's dissipation. And the dissipation basically slows down the jet a little bit, so that the velocity of the jet as it shoots out is a little lower than the velocity of the jet falling in. And if there's less velocity, for conservation of mass, basically you need to have a little wider jet. This is a simple explanation for what you see there. And of course in this paper there's many observations, additional quantitative observations and explanations, and there's energy analysis and so on. There's some calculations of the viscosity changes that need to happen, and etc. I'm going to, for those of you who are interested, put the original paper on Blackboard for you to read. Yes?
I was just wondering, to show the cascade effect you put on slanted surface, can the amplitude of that kind of waveform be calculated based on
Well, this is the explanation. Well, there's a simple balance of energy, right? There's an energy that's a kinetic energy, potential energy, and that will indicate how high the jet will go, and then it will fall down. And so you will see, of course, that because of the dissipation, again, that I just pointed out, those little jumps are going to be closer and closer together as you go down the inclined plane. Does it make sense? Right? So here's a close-up of the turning point in the jet, and here is a diagram indicating that there's this thin layer here of shear thinned fluid that has a lower viscosity. So let's see, there's the stable K effect, and like you expected, see, the little leaps are lower and lower in height, and the distance is also getting shorter and shorter. And that's a dissipation effect. Okay? Now, another very interesting aspect of this phenomenon is that really there isn't a need for a backing plate. The authors of this paper also report making experiments on just a deep pool of the material, and they could observe it in the same way. There was no change. There's no need for there to be a hard surface at the back. And the most amazing thing they did, I think, is this. They repeated the experiment on a soap film. So they made a soap film in a wire. This is like a rectangular wire that you see here. And there's a film of soap, like dishwashing soap, and here is a streamer just bouncing off this film of soap. And here is a close-up look. And let me show you, I have a video of this one, don't I? Yes. Just watch this one for a moment. Yes, basically the end of the K effect happens simply by disruption of the jet that is being streamed out interrupts the incoming jet, and it falls apart because there's a geometry that needs to be sort of adequate. But when you put an inclined plate, they never can really touch because there's the effect of gravity just allowing them to flow apart from each other. And so the inclined plate allows you to have the stable K effect, or cascading K effect. Indeed. And in the soap film experiment, because of the very thin layer, you can see very clearly this area here. And so you can analyze perhaps the images, the video, and get some quantitative measures of what's going on there. Now, even though this paper became sort of quite famous, and this result became quite famous, this is rather recent, the explanation is not definitive. There are some people that disagree with the explanation. And for example, one alternative explanation is that the jet, when it comes in, actually is entraining some air, and the air forms a layer that enhances the lubrication there. Some people explain it that way. So just to indicate that in both this example and the cornstarch experiment, you can still find conflicted explanations. And I know sometimes as a student that can be sort of disconcerting or unpleasant that there is not a definitive explanation for these things. But in fact, well, it's an opportunity for discovering more things. And the truth is, there is still many aspects of fluid mechanics that are open research topics in this sense, that are not explained fully and that still require people to really make experiments and think very carefully about what's going on. And as you have more advanced experimental techniques, for example, the high-speed camera and image processing algorithms and so on, you can revisit phenomena that perhaps were not explained before and apply some new tools, some new models, and come to a new explanation. So, never be completely satisfied that what you read in one paper is the answer, because there may be alternative explanations. And you just need to follow and make sure it makes sense, but always leave a little bit of open space for being convinced otherwise if you find more information. Okay, so that's the K effect. Isn't it great? I thought I had a great fun looking for these videos, and I will put the papers online for you to read if you're interested. There are some derivations there of energy and the change in viscosity and so on. So we're discussing non-Newtonian fluids. The case of the cornstarch and water, the shear thickening behavior, is much less common. It's much more common to see shear thinning. In this case, this is done with simple shampoo. You can do this with soap. Many industrial products are shear thinning. And so this is a very common sort of behavior that you have to deal with as engineers in practice, because in many industries, processing plants, you will have food products, cosmetics, detergents, and so on, industrial fluids that will have this type of behavior. And but of course, water, the most abundant of fluids, is Newtonian. And so what does that mean? Newtonian? Very good. The shear stress varies linearly with the rate of shear strain. And you can imagine that plot that we've drawn before, where you have tau, shear stress, on the vertical axis, du dy on the horizontal axis, and it's going to be a straight line. That's the Newtonian behavior. But there are also some other behaviors. And here is one. This is the behavior of a Bingham plastic. It's very interesting. It behaves as a solid at low stresses, but deforms as a viscous fluid beyond a threshold stress. So if we were to draw a plot in this case of the shear stress as a function of the rate of shear strain, du dy. This would be our Newtonian behavior, right? Let me just draw it as a dashed line. The Bingham plastic will have a linear relationship, but it doesn't start from 0, it starts from a threshold value, like this. And there's this threshold here that we call tau 0. And so what we have is that mu du dy takes the value 0 for tau less than tau 0 and takes the value tau minus tau 0 beyond this threshold. Or we could write it as well as tau equals tau 0 plus mu du dy. And tau 0 is called the yield stress. Okay, and examples. Can you imagine any material that you use frequently that behaves like that? Can you think of anything from your daily life that is like a solid? Yes? Very good, excellent. Toothpaste is a classic example of a Bingham plastic. It just sits there. If you put a little pot, it just sits there in whatever shape you make with it, right? But you squeeze it out of the paste, out of the tube, and you, of course, can put it on your toothbrush. That's the whole point. Mayonnaise is another example. And an application of industrial value is that this behavior is used as a model for mud in offshore engineering. Yes? Yes, there is a difference. The difference is that for a highly viscous fluid, if you apply any stress at all, even if it's minimal, there will be some motion. There will be some, it could be very slow, but there will be motion. Glass, for example, it takes hundreds of years, but it is moving. In the plastic, in the Bingham plastic, for small stress, it just simply will not flow. It reaches equilibrium. It is in all of this range of stress, it is in equilibrium.
Is that a suspension? It seems like most of the things you talked about before were colloidal.
Yes, there's all these mixtures, right? I don't know the details of what is like how toothpaste is made, but there are many cosmetic products and there's a whole chemical engineering branch dedicated to making these products and mixing, making colloidal suspensions, and many times there will be some sort of complex fluid like that, rather than, so in a macroscopic way, in a macroscopic point of view, it's like a fluid, but if you go to the microscopic, you will see particles, or you will see little bubbles or something like that, like mayonnaise, right? It's a suspension as well. And yes, so there's a whole branch of fluid mechanics dedicated to complex fluids in that sense. Okay, so let's do a little example. And I'll put this also on Blackboard for you to have, so you don't need to write down the whole description of it at the moment. Let's just read it. So imagine that you have a lab experiment. So let's try to do this one without writing the whole description again, as I say. And so you have a water flowing on a flat surface, and somebody takes some measurements of the velocity of the water at different heights above the surface. A student comes and analyzes the data and makes some sort of empirical analysis to obtain a distribution, a velocity distribution. U will be the velocity, Y will be the height above the surface. So write down that velocity distribution. The velocity is measured in meters per second and the height in meters. So the questions are, is the expression above valid in any system of units? Why or why not? And can the equation be physically correct? And this example points to a very important use of dimensional analysis, which is it can help you find wrong equations. Like I said in last class, it can help you get better grades in your exams. So have a go for just a couple of minutes with that equation. There's simple length and velocity there in the equation for you to analyze. I'll give you 2 minutes to have a look at it. I see some shaking heads. You have to explain why, though. Do you want to volunteer something? What about that point 31? Yes. What you're saying is that constant in that equation has to have dimensions, right? And this happens very often in empirical relations. The constants that you obtain have a dimension. So let's be a little bit more methodical here. We have U, and U has, let me write this extended out like this. So U has dimensions of length divided by time. Well, this is just a number, so we don't know. Then this term over here has dimensions of length and something we don't know. A number here from our empirical analysis and length Q. So we see that for this equation to be valid, period, each term must have the same dimensions, right? Because otherwise we'd be adding dollars and kilograms. We know we can't do that, right? So everything has to have the same dimensions. So by the looks of it, each little dot here needs to have some dimensions for this to make sense. So we see that this point 31 here, first of all, needs to have dimensions of velocity. Otherwise, it doesn't work. So this guy needs L times to the minus 1. Here we have length. Well, for this to have dimensions of velocity, then it means that the 6.4 that the student found needs to have some dimensions. It needs to have dimensions of 1 over t, right? And finally, this one. Well, we only need one L, so we need to get rid of 2. So length to the minus 2. and time to the minus 1. So each numeric value that appears in that equation has dimensions. And this happens very often in empirical relations. Something to keep in mind when you do lab experiments and you have to, or any sort of research, experimental research, and you obtain empirical relations. Or you find an empirical relation in a book or in a paper. Careful with the dimensions. So the answer is no. This would not be valid in any system of units, because each one of those constants, when you change the system of units, you will need to apply a conversion factor for it to make sense. Yes?
Can you also say something about the nonlinear
The next question is, can the equation be physically correct? Okay, that's the next question. And what do you think? Are you all thinking? Any volunteers? Yes.
like you said, it's not linear that
So it could be a nonlinear behavior, so it could be a non Newtonian fluid, but oh, it says that it's water. Okay, we have a little problem here, right? But there's a bigger problem. Yes. Excellent. Fantastic. That is crucial. The no-slip boundary condition. That is a very important physical observation at the macroscopic level for normal fluids that we know. There are only very special cases where this can be violated at, for example, rarefied gas dynamics, when you have really, really rarefied gases at the microscale and so on, then you can start seeing some effects of the, the molecules actually really atomic level effects. But otherwise, no slip boundary condition always applies, and so this is not correct or valid because it violates the no-slip boundary condition. So there are certain, what this wants to reveal to you is the importance of inspecting. As an engineer, you can inspect and expect. There are certain things physically that need to make sense, and if you look at an equation there, it violates the no-slip boundary condition, it is immediately discarded as incorrect. And those things can be very useful skills, and it only happens with some practice and deep knowledge of your engineering material. Okay? So let's see. Maybe I will take a break here. Let me see if I had something. Yes, it's time. Let's take a little break. Just 10-minute break. And we'll start part 2.